Good morning, everybody. Welcome to this fourth and last session in automatic control. And then we have the first presentation that has a title, Chaotic System Generalized Quasi-Synchronization, and it's presented by Lawrence Oliver. So please.
Thank you. Thank you so much.
Here, the point.
So much.
Okay, you can try it. Yes.
Problem? Okay, it works. Okay. Good morning, everyone. We present this really brief study on generalized quasi-synchronization in chaotic system by Luis Oliva and Rafael and Israel from Automatic Control Department. Here, simple start. Okay. The outline of this talk is really brief. Um, there is no large content. A brief introduction, dynamic controller, is the proposal, numerical example, and some conclusion. Introduction, the chaos in synchronization. We can identify four types of this chaos synchronization. The first type is the complete identical chaotic systems. We can try to synchronize all the functions, but the system is equal, identically. The second is phase synchronization. In some sense, we can try to synchronize the phase of a chaotic system with another signal, a periodic signal usually. A lag synchronization, and in this case, we can take different type of chaotic systems, but the synchronization may present some lag in time according to the synchronization. And then, in the case and its study, the generalizer. In this case, we can try to obtain an operator that maps the functions of one chaotic system to another chaotic system. So we can, when we talk about the chaotic systems, we introduce sometimes a coupling. In this case, we have the unidirectional escape and bidirectional escape. In the unidirectional escape, this configuration usually named as a master slave system. We have one master system and one slave of slave systems. In the bidirectional case, we have two systems, and the system shares information to each other in order to achieve the synchronization. So, what is the meaning of quasi? And in this context, we the synchronization, and in the synchronization case, we try to synchronize the function in the sense of we can obtain a zero error between the signals. But in the quasi of the term quasi refers to try to approximate the function in some region. In this case, the region is signaled in the dashed line. So the properties of the quasi synchronization is we can move and work with this epsilon in order to obtain a really small epsilon. What is the properties? In practical application, the chaos synchronization inaccuracy and lack of information, what is this? Disturbance and parametric type, and so on and so on, are indivisible. In general, this is detrimental to the synchronization quality. There are several papers, there are several studies when we try to obtain a better results in order to the synchronization topic. However, this this lack of information implies some really strong constraints in order to obtain the synchronization. However, the quasi-synchronization relaxes all of these constraints. In this talk, we try to synchronize resistance in the sense of to try to avoid these problems from the lack of information. So we studied the generalized quasi synchronization of chaotic systems under a master and slave configuration. This system which made different dimensions, and the structure of the system may be unknown. So the parameters and the disturbance we can try to handle with this proposal. And what is the main results? We try to obtain or to achieve the quasi synchronization by a dynamic controller. The dynamic controller whose construction does not depend on the structure of the system, and the parameterization of the full controller of the whole controller is straightforward. We also propose an estimator that allows to approximate the structure of quadratic systems, and in order to, along with the dynamic controller, we give a proposal that is robust against parameter uncertainties and disturbance. So the main result is the dynamic controller. We take the two chaotic systems, x dot and the vector field f and y dot. The x is the master system, and y is the slave system in this representation. The variable u is the input control, and in this concept is the dynamic controller. And Aleph contains all the parametric uncertainties, disturbance, and so on and so on. The vector fields f and g are well defined. That is, Lipschitz, continuous, etc. Initial condition are constant, x0 and y0. So we try to analyze how to obtain the dynamic controller result. In this sense, we define the error function like this: y minus x bar, y is bar, x bar. Sorry. This variable is constructed in order to take different dimension. In what sense? We have three cases. The first case, the case A, we have the same number of variables. The master and the slave have the same variables. In the case B, we have master variables. That is, we can take the function. We have more function in the master system than the slave system. And the last one is the case C, and the vice versa. So we have more slave states than master states. And how to complete this function? In the last one case, we consider the function R, a desired function with this condition. So we derive the error function in order to try to analyze how to conform this solution. And we introduce the definition of the quasi-synchronization. Really brief, the definition, we try to obtain a set. In particular case is a compact set, in which the solution of the error system converges syntactically and remains. So, and then this is the details. At this moment, we present the main result, but all the details are in the paper. You can read and without problem. The principal result of this talk is this dynamic controller, simply dynamic controller, and presented the three equations. What is the properties of this dynamic controller? We can tell along this talk. Particularly, we don't need any information of the system, any information of the system. This model free, we can apply without any information of the system. We only need the master variables and the slave variables. So this is the proposal, and the schedule of proof is not difficult, but we can present some pre-steps to obtain the results. We take a quadratic function, derivative, all of the Lyapunov theory. At this point, what is the main result of? In this case, we only obtain this bound, mu. So this mu is particularly the bound of the set that that the definition of the quasi-synchronization contains in this set. So, and from the theorem, we have a direct consequence, corollary. All the functions in this equation, in this dynamic controller, are related to the norm of the error function in the sense of error. All the details are in the paper. There is no more problem. So we can take the parameterization. In this case, from the analysis, we obtain this relationship. This matrix gamma satisfies, or maybe satisfies, Lyapunov equations, simple Lyapunov equations. There is no problem. In this sense, we propose that this is the parameterization. All of these details is in the paper. There is no problem. With this selection of gamma 1 and gamma 2, we satisfy the Hurwitz condition, the boundary condition, and the set that obtained from this parameterization is this, where the error function only depends on delta and theta 1. Theta 1 is constant, simply constant to positive constant. So from this point, we parameterize the whole controller, and we analyze the dynamic controller. We only avoid this term, that this term is an estimate of the on-off of this vacuum information, disturbance, so on and so on. This delta, we propose to use some sample estimator. So this estimator is an algebraic estimator. There is not the information. It's simple to apply. No more problem. So we have a proposition from this estimator. In this case, the estimator represents from this equation, 15 equation. There is no more problem with this result. There is a proposition, all of the details in the paper, no problem. The set, the final of the set obtained is the following one, where this L and this theta are the parameters that only we need to impose in the controller. There is no more problem. We this set provides a selection criterion for the parameter L and the parameter theta. In order to increase, we obtain a lower bound for the error function, for the normal error function. This estimator equal to the dynamic controller doesn't not need any structural properties of the chaotic systems. So
we have 2 minutes.
Okay. Numerical result, a simple chaotic system, Van der Poel and Roller hyperchaotic system. The Roller system, we have only 2 variables, and Rosler, we have 4. Well, first, for the hyperchaotic case, we have 4 variables. So this chaotic system may have many applications. For instance, in the Van der Poel case, we can modulate the heart rate, and the hyperchaotic system usually is referred to the chemical reactions. So on the parameters, these parameters may uncertain and may have some disturbance. The decided function, y decided function, we have more slave variables than master variables. The error function, the variable delta, and obviously the parameterization, only 2 constant, theta 1 and L, 115. Initial condition and the results. We have to obtain the quasi-synchronization in this case to the Rosler system and the Van der Poel system, and obviously the decided functions for the variables y3 and y4. The estimates, usually the more problem to estimate this variable, and the behavior of the first component of the dynamic controller. So, in conclusion, we propose a dynamic controller that doesn't not depend on the structure of the system, that is achieves the quasi-synchronization in the chaotic system with different dimensions, The parameterization of the whole technique is simple, it's straightforward. The analytical proof supports these results and is along with the numerical results indicate that the dynamic controller and estimator are effective, robust, and so on and so on. The range of applicability for this proposed is huge, for example, and data encryptation, signal encryptation. So thank you so much.
Okay, so we'll talk about that speaker. We have time for questions. Is there any question? Yes. Actually, now with your numerical example, I understood some things, but well, first one observation, and actually I got the same remark 2 years ago in one conference in Europe. Now master slave is like inappropriate. It's not politically correct. So they suggest now to use leader follower systems because it's a bit now. Now the other, when you explain the generalized concept of synchronization, you say that there is a mapping that relates the leader and the follower states somehow. Can you put the slide number 10, please?
Yes. And in the definition.
Yeah. 10. This is 11. Yeah. When you define this extended state X bar, you are taking the states of the original leader system, that it can have the less states than the follower. So to have correspondence on dimensions, then you add these R functions. In this point, you put that these R functions are time dependent. Could it be state dependent or not? I mean, depending on the other states of the leader system.
Yes,
or not.
There is no problem to consider this desired function. So we can put this function in, to depend on the states with this condition. This function should be C2, and we have its at least second bounded derivative. All of these conditions in order to analyze the operator and the corresponding bound works.
Yeah, I was wondering somehow, and actually I thought at the beginning, why not to put then just 0? That's the case you show on the numerical simulation. But I was wondering, in case like there is a sort of combination on the master systems, could it be the case like the desired behavior of the leader signal, systemic signal? What happens if the system is not completely controllable, and then those signals are out of the span of the function of the chaotic system?
Yeah, we
have to guarantee that those functions are doable or just achievable.
Also to work with them.
Yeah, that's why I was wondering there was some conditions on those functions.
Exactly.
And yeah, the other part is because I was wondering, what if with the master states you make a linear combination?
Yeah.
And then I was wondering what happened if that combination is not achievable by the
linear
system. Interesting. And a very common application of these systems is encryption in communication.
Exactly.
But I was wondering, when you have this mapping, you mentioned, if you put the figure when you explain the generalized, it's like at the end, you are not, no, when you define the generalized, I think it was like 6.
6. It's like 6.
Yeah. It's like you don't converge to the real estate of the leader system, but to an epsilon around it. So what could be the effect in this kind of application, like communication, when you really need some robustness?
The complication or the implication of this epsilon, when we have we need to robustness in the application. We think in the there is some about some information we have to lack information from a signal to in the application case. But this epsilon corresponds to this bound, in this slide, we can put this epsilon. However, we change the notation. Also, in this case, this epsilon refers to this term. So with this variable, we can to reduce this term in order to reduce the size of
epsilon.
Exactly.
Vicinity.
What is the consequence?
Yeah.
These variables put in the controller.
There's no free lunch.
Exactly.
Okay, thank you.
Thank you.
Thank you. Okay, so we have a second talk of the session. Is Jose Medina here? Okay. Is the pointer? But actually, the pointer is not working because of the screen, but you can, move from slide to slide. So wait there for the presentation to be shown. Ahorita que se ponga la presentación. Con esto. ¿Sí está cargado? Sí.
Creo que sí, bueno, es que no lo pone.
No. Si es que el láser sí funciona acá, pero en la pantalla se pierde. Pero para pasar las transparencias, ¿no? Es que cargue. La propuesta.
Pues no. Bueno, ya la presentación.
In this session, it has the title Nonlinear Oscillations with Linear Solutions. The speaker and author is Jose Medina. So please, you can start.
We begin became the aim of the talk is exploring a family of nonlinear oscillators that share phase plane trajectories similar to the produced with linear systems, but the difference is we can generate completely different periodic waves. Well, we have some examples of the power of oscillators in several areas. So, here are some of the most famous nonlinear oscillators in some areas like engineering or biology and chemical systems. This is the basic system that produce. This is the basic linear system with that we are using at a starting point. See, for the production of linear oscillators. This is a generalization of the system for producing mechanical waves in a nose spring system like this. We have only C and A different from 0, D and B equal to 0, we have this type of differential equations. And it can be proved that we have this Hamiltonian. And so the solution of this equation is this curve in the plane. Here we have the figure of the solution curve in the phase plane. This is a typical trajectory of a linear system. But if we use this structure with D and B different from 0, we can construct more general oscillators like this. This is the phase plane also, but we have these component functions different from the traditional sine and cosine functions. It's on a sheet along the vertical axis. If we change the parameters of the initial model, these parameters, A and B, we can construct another oscillators like this. And these are the components. And here we choose a G function that is not 0 in the plane. We can construct non-linear oscillators. And it can be proved that the solution curves in the phase plane are the same. That the linear system obtained with taking G equal to 1. It can be proved analytically in mathematical form and using numerical simulations. Here we have the case when G is equal to 1 minus x squared. See, here we have the solution in the phase plane. And here we have the components. Here we can see the effect of the nonlinear factor. Here are different from from this. And here we take a different function G like this. We continue having a solution curve in the phase plane similar to that produced with a linear system, but the components are very different. So the use of this factor can serve to produce periodic waves, but with very different forms. Or we can use a fixed system, a linear fixed system. But if we change the G function, we continue having the same phase plane, that we can have an infinity of component functions, periodic. See, every linear system can produce an infinity of periodic components, changing the G function. So depending of the use of the periodic function, we can get or we can search for some useful G function, or create a catalog of G functions for generating a set of nonlinear functions for different use, like indicated in this area. So here are some conclusions. Basic linear oscillators known in the literature can be be considered like belonging to a broader family of the basic importance of this is the use of key factors. It can give us a infinite family of nonlinear periodic components.
Okay. Well, we thank guys. Any question? How would you identify some conditions on the G function, like to preserve that behavior of the original oscillator? I mean, I guess it has to be continuous, differentiable, or could be any kind of G function.
The only condition is that the G function not to be zero in the plane or near of the solution curves of the system we are considering. That's the only, no zero, obviously continuous, differentiable for the existence of the nonlinear system.
Okay. And have you tried out to produce chaotic behavior through this G function? I mean, not maybe. I mean, I think that the goal is to preserve the original oscillator behavior. That's true. But have you tried out maybe to create some other behaviors through this G function, or is not the purpose of your research?
And I have tried to use another G functions. See, I did a probe with about 5, 7 functions using a numerical program, and also I get the same. I got the same condition. See, the the numerical simulation gave the theoretical results indicated in the paper. See, it's una. I say at the beginning I don't believe that. See? So I use the numerical program y that confirm that the result.
Okay. Any question? No? So we thank the speaker. Thank you very much. And we have a few minutes before the next presentation. We have 4 minutes. Coffee time. Who is the speaker of the third presentation? Distribution event trigger. Is here or it's online? It's online? Ella ya la va pasando. To continue with the presentations scheduled on this automatic control session, we have the talk entitled Distributed Event Trigger Estimation over Sensor Networks for Satellite Tracking in LEO. The speaker is Laura Adriana Galicia. Is that correct?
Yeah.
Okay, please turn on your camera. Is that ready?
Okay.
Okay, perfect. And you can start, please.
Okay. My name is Laura Galicia. I am affiliated with Tech NM Senidad. I am delighted to present our undistributed event trigger estimation over sensor networks for satellite and tracking in LEO. I would like to thank my co-authors from Tech NM Senidad and Tech NM Tecnológico de Hermosillo and the conference organizers for this opportunity. I will structure my representation as follows. First, I will introduce the research context and challenges. Then I will present the problem state and our observer design. Next, I will explain the event trigger mechanisms and theoretical guarantees. After that, I will show the satellites tracking case study in the simulation results. Finally, I will conclusion with our main findings and future work. And distributed estimation plays a fundamental role in modern technological systems. We find essential application in autonomous vehicles where multiple sensors must locate and navigate collaboratively, and in environment monitoring networks that track pollution or weather patterns, and in smart power grids that require real-time state estimation across widely distributed infrastructure. These applications share common challenges, the need for scalability, fault tolerance, and efficient use of resources. The same challenges arise as space system, which leads us to our specific research focus. We are investigating distributed estimation for tracking satellites in low Earth orbit because this region is home to a growing number of satellites constellation that require accurate relative position and collision avoidance capabilities. When examining centralized approach in practical application, several critical challenges arise. Computational overload becomes apparent in single estimator must process data from many satellites, simulators. Processing demands because unsustainable scalability limitation are even when considered that adding in single new satellites to a central system could require a complete architecture. Communication models manifest themselves in the form that delights in time-critical application, where waiting for data to travel central node can resolve missed opportunities or even collision. Is this limitation that drive our research toward distributed estimation solutions that can grow incrementally and manage failures that may occur? Let me now address the research graphs and our specific contribution. If we examine existing work in distributed estimation, we found several important limitations. Most approach assuming indirect or static networks, which doesn't reflect the asymmetric nature or real-world communication system. They are often limited to symmetric information flow and suffer from high communication overhead due to continuous data cache. Additionally, validation is typically limited to numerical simulation without practical case studies. Now, looking at our contribution with these diagrams, we see our direct network topology, analyze traditional unidirect graph. This allows for asymmetric communication partners that better model real-world scenarios where information flow isn't necessarily bidirectional. The second diagram illustrates our observable and observable decomposition approach. Here, the complete system state decomposition into components that are either locally observable or require cooperation between nodes. This composition fundamentally simplifies our convergence analysis and enables structure gain computation. Our node innovation include a dynamic event trigger mechanisms that reduce network traffic by transmitting data only when local estimation errors excite adaptive threshold, which validates this framework through a satellite formation case study. Moving beyond purely numerical validation. In addition, we achieve communication reduction compared to periodic strategy while maintaining exponential conversation guarantees. And its contribution directly addresses the limitation with identifying direct graphs overcome symmetric flow constraints. Event trigger eliminates continuous communication, and the decomposition of states allows of easier analysis. Our baseline, a linear system where the state evolves through matrix A and is influenced by impulse through B. While can only observe the system through output matrix C. In our distributed observed architecture, the state it combines local model-based prediction with measurement correction and neighbor cooperation. And shown by dotted communication lines in the figure, neighbors sketch estimates only at the moments when an event occurs, not continually. This means that its observer use the most recent reliable estimates result from neighbors rather than the latest available data, but our design ensures commerce through appropriate gain selection and strongly connect direct network topology. Our event trigger mechanism works like an intelligent communication manager. Each observer continuously monitors two things: how much its local estimate has changed, how in comparison to neighbors. Communication occurs only when local changes become significant relative to an adaptive threshold that itself evolves based on network consensus. This dynamic threshold automatically adjusts, become more lenient when neighbors agree, and stricter when disagree emerged. The result is that we maintain estimation accuracy while reducing communication compared to continuous strategies. Our main theorem states that under global observability and strongly connect direct graph with our event communication, we can design appropriate gains in ensure asymptotic converge to the actual state of the system. The theoretical basis of our work is supported by several key innovations. We begin by the decomposing the estimation problem into what each node can see individual versus what requires collective intelligence. This composition, achieved through orthogonal transformation, allows us to design specific gains. So for local correction, others the network concepts. The current condition provides a mathematical guarantee of stability. It tells us exactly how strong the network coupling must be in the relation to the system dynamics to ensure that local estimates converge to the actual state, even with or even triggered communication.
You have 2 minutes left.
Oh, let me now word you parts. Equation 5 is error the observer. Equation 6 is the error the communication. The 8 and 9 is the decomposition, observable, unobservable. The portion is TM. The observer errors prevent the conversation asymptotic to zero. Now present research problem, distributed satellite orientation estimation. The research address the challenge of maintaining precise attitude. Where objective is to design in event trigger distributed estimation framework that minimize communication overhead while maintaining attitude consensus. The equation thing are closed with dynamics. The system parameters six external model position and velocities. Three distributed observers. The graph strongly connect directed. Here, the matrices A, B, C, the matrix C, partition C1, C2, and C3, only jointly, but observability.
You have 1 minute.
Okay. The position estimate results, and event status 77 events, reduction 99.5%. And conclusions, distributed survey with event communication for linear system, significant reduction in internode, and synchronous activation with adaptive dynamic thresholding, experimental validation in lieu, Porsche satellite scenario, and maintain exponential converge with reduced communication. And this future research direction extension to multiple satellite system and another sensor networks. And this reference. Thank you for your attention.
Okay. We thank the speaker. And we have time for a short question. Any questions from the audience?
Okay.
Well, if I understood well, the event that triggers the observers in this case is the error that you have in the system. Is that right?
Okay.
Yeah.
But
what I was missing is because you are just focused on that the observer design, but the error comes, I don't know, from the regulation problem or a tracking problem, or as in this example that you mentioned, is a sort of synchronization or formation. How do you decide the threshold that is acceptable for the system to trigger this observer condition?
Bueno, dynamic, I have one dynamic threshold variable is for equation. Compare estimation error state and error communication. This major, then dynamic trigger condition trigger. This variable is my help for dynamic trigger condition.
Okay. Thank you. Any other question? No. Okay. Thank you once more. Thank you. And we have a change in the schedule. We had a last presentation that was moved for another session. And yeah. The title of the presentation is Adaptive Real-Time Neural Control for Permanent Magnet DC Motors under Uncertainties. The speaker is Ivan Urbino, correct?
Okay.
Yes.
Hi, and good morning, everyone. I'm about to present the walk titled Adaptive Real-Time Neural Control of Permanent Magnet DC Motors under Uncertainty. My name is Ivan Urbina, and the content of the presentation is distributed as follows. We're going to start with introduction and literature review, then continue with some preliminaries, specifically the motor model and the neural network that we use modeled. Then we're gonna have the controller design and the stability analysis, following with the results that are divided in simulation and real-time implementation results. And finally, to end with some conclusions and the future work. So the introduction and literature review. So permanent magnet DC motors are widely used in industry applications, but the main problem to use them and to control them is that in almost most cases the parameters of the system are unknown or partially known. And with some previous work have developed novel advanced control techniques to overcome these parametric uncertainty. These advanced control techniques include fractional PID controllers, also the use of neural networks to indirect control those systems. Some of them are based on multi-layer perceptrons, and some of them with recurrent neural networks. The use of neural networks in automatic control is divided in two main approaches. The use of the neural network to first model the system and then control it. But in this work, we are proposing the use of the neural network to directly compute the control signal UK. Also, this neural network is trained online with the use of extended Kalman filter. So the preliminaries of this work is the motor model. So the model is defined in equation number 1. It has all the parameters like the stator resistance, the inductance, and another constants. So the model is obtained after applying the Kirchhoff voltage law and Newton's law of motion to the equivalent circuit that is shown on figure number 2. The description of each parameter is provided in table 1. Here it is important to notice that those parameters were found by experimentation, so it means that they have uncertainty. But we use those parameters to design a PID controller to compare it with our neural approach. So after discretizing the system using the zero order Hall technique, we obtain the state space that is shown on equation number 2. So then we have the recurrent high order neural network model. So this type of neural networks are mainly used to model nonlinear systems. But we use it to, as I said before, we use it to directly compute the control signal. So the main difference between these neural networks and the regular recurrent neural networks is that these neurons usually have products of the inputs and also the use of previous outputs of the neuron. Uh, the main advantage of this architecture is that it helps the neural network to model more complex interactions between the inputs. So the description of all the architecture is can be seen on equation number 3 and number 4. So then we continue with the controller design and the stability analysis. So if we use the dynamics that were shown on equation number 2, we propose the use of a neural network that receives the reference signal and the output of the system. So if you remember, we were talking about a permanent magnet DC motor. So the reference is given in radians per second, while we have a sensor that is obviously sensing the actual motor speed. The weights are square on the red square. So those are the constant, I mean, no constant, the dynamic weights that are being online adapted with the extended Kalman filter technique. The online training algorithm for this network is described on equations from 5 to 7. We calculate that the weight of the next step is given by the Kalman filter gain dynamics that are shown on equations 6 and 7. It is important to notice that this extended Kalman filter is receiving the tracking error that is defined on equation number 9. In order to verify the convergence of this neuron using the Kalman filter and as ways as to use it to minimize the tracking error between the reference signal and the actual system output, we use Lyapunov theory. On equation number 10, we propose the use of a quadratic function of the weight, and after finding the discrete time derivative and substituting the Kalman filter gain dynamics, we found exponential convergence and proving that the neural weights are bounded. A more specific approach was used to prove the whole system stability, resulting in exponential convergence that follows equation number 12. So the results, the proposed controller was compared with 3 approaches: a traditional PID controller, and as I said before, this PID controller was synchronized using the parameters that are not the correct ones, because that's all we know about the system. The use of a multi-layer perceptron and a recurrent neural network controllers. As you can see on the left side of the screen, we have the error evolution between all approaches. The recurrent neural network, the recurrent high order neural network, is the one that outperforms all of the approaches. On figure 6, we have a 0.2 window showing the reference tracking comparisons between all the approaches. As the paper title says, we did a real-time implementation with the following hardware components. We use an Arduino Uno. We use a DC motor with that specific part number. we use an L298N dual H bridge to amplify the PWM signal that was computed by the Arduino Uno. And we did a custom built motor base in order to mount all the experiment. So figure number 7 on the left shows the real-time error evolution, while the figure number 8 shows the real-time reference tracking comparisons. As you can see, the performance of not only the recurrent high-order neural network controller, but to all of the controllers was way worse in real time. Because in every dynamical systems, when they are implemented in real time, some unknown dynamics may appear. In order to measure each controller's performance, we introduce or we use 5 metrics. ITAE, ITSE, IAE, ESE, and MSE. Table number 3 shows the value of all those metrics after 1 second of real-time implementation. And the values that are highlighted on the table show how much our approach, the recurrent high-order neural network, was able to reduce compared to the other controllers. It is important to notice that the closest one was the recurrent neural network controller. That is because recurrent high-order neural networks are just an extension of regular recurrent neural networks. Figure number 9 shows real-time performance metrics, where you all can see that our controller was the best performing one. Finally, we have conclusions and future work. Starting with conclusions, we have that recurrent high-order neural network controllers have superior tracking compared to PID controllers, multi-layer perceptrons, and recurrent neural networks, as is shown in table 3. The extended Kalman filter, the use of extended Kalman filter as an optimizer avoids the use of back propagations computational cost, because it sometimes is hard to implement it in real time in an embedded system such as an Arduino Uno. The use of this framework has a balance between control precision and dynamic adaptability, because as I said before, this neuron is trained online. So it means that if we change the plant and if we put another motor in, the network is going to adapt to it. So we don't need to know all of the parameters of the system. Some future work includes extend this approach to highly nonlinear systems such as BLDC motors, chemical reactors, or hydraulic plants. We need to evaluate this approach to more complex dynamics. And the future work number 3 is to explore alternative training algorithms, such as those based in sliding mode methods like super twisting algorithms, to explore spin time convergence. We are currently working on future work number 1 and number 3, because we are trying to extend this to a VLDC motor trained with a super twisting algorithm. So here are some of the references that were used in this work. And that's it for my part. Thanks for your attention.
Thank you very much. We can repeat that. We have time for questions. Any question?
There are no network. You need some measures of the motor, like position or velocity.
Use angular velocity.
Only angular velocity.
Yes.
How are you measuring this variable?
We use an encoder.
To an encoder to measure velocity.
Yeah. Yeah, we took samples through a specific time lapse and then divided by the time lapse and then
Okay.
the
So
angular
you're
velocity.
estimating the velocity,
Yes.
the angular velocity. How many layers does the neural network have?
It's a single
A
neuron.
single neuron.
Yeah, it's a single neuron.
Only a neuron.
Yes.
So you need the neuron and velocity to do control of position or only control of velocity.
This control velocity.
And the experimental results, the motor have some disturbances or is in the disturbances free case?
No, it has disturbances on the paper. It is the tile. It is the tile because we tried to put some load on the motor and we measure how the controller response was.
And the control strategy has the best performance in this case.
Yes, it does.
Okay, thank you.
Any other question?
Just one more. As we can see in your future work, one future work, you try to extend to nonlinear systems.
Yes.
Why not this time? Because you are using neural networks, extended kernel filter. Why not this time? What changed in the nonlinear case?
The main reason was because when we developed this work, we didn't have a nonlinear plant to work with. We only had a regular DC motor, but we currently have a VLDC motor, and it's the one we are working with.
But usually DC motor have a nonlinear model. You can apply a nonlinear model because you have loss of energy, some types of nonlinear signals to apply in the model. All of the models are nonlinear.
I mean, yes, a regular DC motor can have a nonlinear model, but the linear model is a really good representation of the plant system.
But only in some in some region where you obtain the linear model. What happens if you suppose the case in your DC motor pass away in the temperature from the magnet, for instance.
Yeah, because if the motor overheats.
So,
Yeah, if the motor overheats, it gets out of the linear region and it starts to behave more like the non-linear model.
okay.
But that's why we are using the neural network, because it adapts online. So even if there are changes to the model, the neural is still adapting to those changes.
Any other question? Thank you. Now that you explain, like you have only one neuron, and then you say, okay, this is real-time feasible. But when you will have a non-linear system, maybe it's not going to be enough with only one neuron, and maybe you will even need some extra layers on your network. So in those cases, sometimes it's there's not enough time for the neural network to converge for the time you need the input for the sampling. I don't know, you didn't explain here or you didn't mention what is the sampling time you were using at the
Yeah, it's shown on the parameters table.
Okay.
We use that sampling period.
Okay, well, it's high enough. Yeah, because sometimes when you have really nonlinear systems or complex systems, even with a higher number of states, there is a problem of not fitting the time of the neural network response to the sampling that you need for the system. And motors are usually very high-speed systems in that sense.
Just so for the case of the BLDC motor, we are having three neurons.
Okay.
It is one for each motor space, and we also have another one to model the mechanical behavior. So we have three neurons for the electrical part and one neuron for the mechanical part. So yeah, as you say, one neuron is not enough to model a more complex system.
And what about the standard Kalman filter in that case? How do you ensure like the good behavior of the standard Kalman filter for a higher or complex system?
That's why we are switching to the sliding mode methods to train the
Yeah.
network.
Okay. Thank you. Any other question? Okay. Well, we can. With this, we finish this session on automatic control. So now we have 10 more minutes, and then there is going to be a plenary talk. The last session of the conference. Thank you for your assistance. Gracias.